Hello everybody, today we're gonna discuss about principal component analysis using our software. Before skipping to our analysis, better to say something about PCA. PCA allow us to summarize and to visualize the information in a dataset containing a number of observations that are described by multiple interrelated quantitative variable, and each variable could be considered as a different dimension. And for example, if you have a number of variables, let's say 10 variables in a dataset, it could be really difficult to visualize a multi-dimensional hyperspace. So principal component analysis helps to extract the important information from a multivariate data table and to express this information as a set of a few new variables. It's called the principal component, and these new variables correspond to the linear combination of our original variables or original data set. So the number of principal components is usually it is less than or equal to the number of original variables that you have. For example, if you have 10 variables, your PCA is equal to 10 or it is less than 10. And as all of you know that the PCA helps to reduce the dimensionality of multivariate data into 2 or 3 principal components that can be visualized graphically, yes, in fact, with a minimal loss of information. As all of you know that the principal component analysis is particularly useful when our variables that found in our datasets are highly correlated. And this correlation indicates that there is a redundancy in our data. And due to this redundancy, the principal component analysis can be used to reduce the original variable into smaller number of new variables that we call it the principal components. These principal components explain most of the variance. Some may limit around 80%, 70% as a good. This in fact depend on your degree of accuracy. But this principal component explaining the most of the variance comparing to the original variable. And the main purpose of the principal component analysis is three things. First, it helps to identify hidden patterns that found in our dataset. Second, it helps to reduce the dimensionality of the data by removing those redundant or by removing the noise and the redundancy in our data. And lastly, it's obvious, it helps us to identify correlated variables. And the principal components, in order to determine the number of principal components, calculating or knowing the eigenvalue is must. Mostly, an eigenvalue greater than 1 indicates that the PCA accounts for more variance than accounted by one of the original variables in standardized data. Standardized data means maybe you may have 10 variables. Out of 10 variables, for example, a plant is measured in terms of centimeter, grain yield measured maybe in form of ton or maybe in the form of kilogram, harvest index is unitless, biomass yield is in gram, again in kilogram, sorry, again 1,000 seed weight or 1,000 kernel weight maybe is measured in gram. So we have different units. So in order to have a good PCA result, we have to standardize your value in order to get to 0 and 1. 0 means when we standardized our variables to have a mean of what? 0, and to have a standard deviation of what? 1. So standardization means just in simple terminology or in a simple explanation, making your mean to 0 and making your standard deviation into what? Into 1. In addition to the eigenvalue, most of the time you can account the variance component. For example, if you add the variance of different principal components up to 70%, maybe it's good for you. Maybe some other person may like to have 80% or 90%. That is depend on your degree of accuracy. So you can limit the number of components to that number that account for certain fraction of the total variance. For example, if you are satisfied with 60% of the total variance explained, then you use the number of principal components to achieve that. Maybe if you want 80%, so you'll select the number of components to achieve that. So this is depend on your degree or the level of accuracy that you want. So this is the short definition or the short brief of the principal component analysis. So let's start our analysis by importing my data set, which is found in the download. Then let's import it. Yeah. As you can see here, my data contains 12 columns and 19 rows, and the first column is represent the genotype, the last column represent the environment, and the remaining starting from the column 2 and with column 11 that are my variable or response variables. So in order to run the PCA for this tutorial, you have to incorporate all this package to our software. Then after, as you can see from our data contain both the character as well as the numerical value, and the row names are designated by a number. So in order to carry out the PCA or the principal component analysis, the row number should be converted into other name, because this number will be appear in our PCA biplots or graphs. So that's not good for us. As a result of this, we have to convert, for example, row number 1 will be changed by ME, then by this, and the last row name will be changed again by this. So type row names, then you have to indicate the data name. In our case, our data name is GGE, then we will change all the row names by this. So type this and feed to our studio, then let's see our data. As you can see, the row number is converted into our name. So that in order to go or in order to carry out the principal component analysis, you have to use the function prcomp, then it's followed by the data name. And as you can see here, I limited the data to be analyzed from column to 11. The reason why I'm doing this is PCA is only work for a numerical character, and when we see our data, which is contain both the character and numerical value, so I enforced R, or I am telling to R to analyze by starting from column 2, which is column 2, and with what column 11, because this contains what the numerical value. So by this way, I can tell to R and scale is equal to true. That helps us to standardize our value. Standardization means to have the mean is equal to 0 and to have a standard deviation of what? 1. So type this and submit to our studio. Then we are expecting 10 or less than 10 principal components, as I described in my introduction. The number of principal components to be produced is related to our number of variables. So since our variables is 10, so we're expecting less than 10 or equal to 10 principal components. So type this and submit to our studio. Then we will get 10 principal components. The next step is selecting the principal components on the basis of two things. The first one is using the eigenvalue and also their cumulative variance proportion. So let's check how to select using eigenvalue. In order to do that, you have to use the get underscore eigenvalue, and you have to put PCA here in the parentheses. PCA means what we created this. So type this and submit to our studio, then you will get your eigenvalue. So we'll consider eigenvalues that are greater than 1. As you can see, the dimension 3 contain have eigenvalue of 1.56, dimension 2 2.66. Again, dimension 1 contains 3.327. So by this way, we will select the 3 components on the basis of eigenvalue by considering eigenvalue greater than 1. Again, You can also use the cumulative variance percentage. In this case, you can limit, for example, if you say that 70% of observation, 70% of cumulative variance percentage is enough, so we'll select the 3 principal components. But if you want to get greater than 80%, so you are enforced to select the first 4 PC component, principal components or dimensions. So by this way, you can determine the number of principal components. Furthermore, you can draw also the scree plot that contains the cumulative variance proportion. In order to do that, you have to use this function, which is built in the factoextra package, while the prcomp is built in the rstat package, which is a base package that already built in our software. So to do that, to get the scree plot, type this command and submit to our studio, then you will get this result. So the first 3 component, if you add, for example, 33 plus 26, which is around 59, actually there is 1, so around 60, then when you add 15.7, it will be 75.7. So if you are satisfied to select when the percentage of explained variance proportion is reached 70, so you will go for the first 3 dimensions. But if you are not happy with 70%, maybe if you just select your 80% of the proportion, so you have to select the 4th dimension, because 75.7 plus 9 is around 85 point something. So by this way also you can determine the number of dimensions to have. The next step is getting of the principal component result for the variables. Again, also you can also use for the individuals. Variables in our case means like let me show you: plant age, biomass yield. This up to this are our variable. Then by this way you can get the PCA results by typing get the principal component for a variable. And again, if you want for the individual, so you have to change variant to ing. So type this and submit to our studio. Let's see the most important. By the way, you can also get, for example, var, then select the coordinate, again the correlation, again the cosine square, again the contribution to the dimension. So by this way you can go for that. But let's start our business by looking the most contributing variables for each dimension. So to do that, you have to use the corrplot function, which is built in the corrplot package. So you have to say here is corrplot, then you have to use the var. Var means principal components that contain for the variables. Then you have to use the cosine square. Then if you submit this, you will get this result. So yes, as you can see here, the point, for example, for the dimension 1, the NSP, that means NSP stands for number of seed per spike, harvest index, and straw yield, SYHI, are strongly, or they contributed largely comparing to the remaining variables in the dimension 1, and this followed by the biomass yield in the dimension 1, and it's continue for the plant head for the dimension 1. This shows their contribution, but the remaining, that means the SL, the FT, NFT, and TT, and TSW are somehow contribute lessly. When coming to the dimension 2, the pH as well as the SL or the spike length is contributed more comparing to other variables. And again, when you check the BY is second to pH and SL, it also contributes to dimension 2. And coming to the dimension 3, the FT as means the fertile tiller, and again the total tiller in the dimension 3 is contributed more. And when you come to the dimension 4, the NFT, and it's followed by the 1000 seed weight. So by this way we can just see the contributions of variables to different dimensions. Let's continue to other thing. The other is you can also get the that means to see the most contributing variables for each dimensions. For example, if you want for the principal component, and if you want for the principal component 1 and 2, and also principal component 2, you can do in this one. And for both dimensions, you have to use the axis is 1, and then this use this syntax. But if you want to see only for the principal component 1, so you have to suggest here axis is equals to 1. All things are the same. So type this and submit to our studio. Then let's see our graph. So accordingly, as you can see here, for the principal component 1 or for the dimension 1, hi provide the highest, followed by this, followed by this, followed by this. The red line are the mean contribution. As you can see, the rest, that means pH up to NFT, are below the minimum contribution. So by this way, you can deal the variables that contributed for the first dimension. Coming to the second dimension, so you have to use the same, but you have to change the axis or the principal component into 2. So type this and submit to our studio. Then you have to run this one. Yes. In this case, that means in the dimension 2, the spike length, the plant height, and the by are significantly contributed to dimension 2, but the rest are below the mean. That means the mean value. That means starting from NSP tends to TT. So SL, pH, and BI significantly and highly contributed to dimension 2. Then after, you can arrange both contributions in one, but before going to that, for example, let's say if your number of variables is around 90 or 20 or 30, if it is that, it's too high. So you can use, for example, you have to add top is equals to 5. So when you write this, it will only display for the 5 variables only. Yes? Yeah. As you can see, it's only display 5 variables. So you can limit the top function or the top code for limiting if you have large number of variables. But let's back to the original one. Yes. So that's this. Then you can arrange both the PC1 and PC2 in one graph. If you want that, you have to use the grid.arrange function, which is built in the grid function or in the grid package, as you can see here in the gridExtra package. This helps us to arrange both plots in one form. So you have to use the grid arrange. Then you have to type here is A and B. A means the axis that contain the variable that contribute for the principal component 1, and the B, E, here is the principal component that contain the second principal component. So by this way you can arrange in this way. Yes. So both of them are displayed. The first one is the variables that are contributing for the dimension 1. The second one is the variable that contributed to dimension 2 or principal component 2. Then if you want to see the total contribution for both the principal component, that means PC1 and PC2, so you have to use again this function. That means here is not a variable but the individual. That means individual in our sense is the row names. So MEE6, that means this represent for men's genotype, this represent ETBW9436 genotype. So if you want to see that the individual one, so you can type and this So submit to our studio, then it will show you the genotype that contributed for both the principal component or for both dimension. Accordingly, starting from EA2 end with AB significantly and above mean they contributed for both principal component, but the rest are starting from DI and with this genotype is less contributed for the two dimensions. Then again, if you want just to get the graph of variables only, so you have to use the PCA var and you have to indicate here is the PCA what we created in the model. That means using the prcomp function. Then color of variation is cosine square. The gradient of color, that means the red with weak, the blue with medium, and the green with high selection. So repel is also true. This helps us to text overlapping. So type this and submit to our studio. Yes. So the green one is, that means, for example, those have the color of, for example, here is the green, here is the green, here is the green. So this means these variables are highly correlated, while the red one is their correlation is weak or somehow is no correlation, but the one with green light or green something is look like a green, but it's not as such as highly correlated, but it is somehow is medium correlated. So by this way you can get this clue. For example, all variables except pH and DSL are found in this axis. That means they are positively correlated, but if they are in other side of the graph, indicate that they are a negative relationship with this variable. So if you check planted with by, SL with this one, and this with others one, so you will get a negative correlation. But their color is, well, the one that you get with green color means it is a strong correlation or strong association. So by this way you can do variables in this way. Then again, if you want to create a biplot of individual and variable, that means the genotypes as well as the variable together. So you have to use, here is the PCA biplot, that means containing both plot. Then you have to use the PCA repel, that means it helps us to avoid text overlap, and the color variable is equals to blue. So the variable will be designated by blue and the color of individual designated by red. So type this and submit to our studio. Then you will get this PCA biplot that contains both the genotypes and our variables. So by this way you can display both the variables as well as the genotype together in this form. Furthermore, if you want to create the biplot using the ggbiplot package, so just type simply ggbiplot, then PCA. So you can get such type of variables name in our software. Then the principal one contains 33.3 variation, while the PC2 contain 26.7. So by this way also you can display the PCA using the ggbiplot function. Moreover, if you want just to get the including with the individual, that means the genotype or the row names, so you have to use this function ggbiplot, then PC labels equals to row names, and you have to indicate your data name. So type this and submit to our studio so that you can get the genotype as well as their trait in this form. Then if you want to plot, for example, we get around 10 principal components. If I want to draw using the first two principal components, so I will choose 1 and I will choose the first two, so I will type 1 and 2 in this way. Then row names will be gg, then the group will be environment. As you can see here, there are different groups: Jimma, Malkasa, Raya, and Adit. So I will group on the base of this environment, then I will run, or I will submit my command. So again, you have to use here is ellipse is equals to true, then I will get say type of plots. So the red color is designated by added. Again, Gemma is somehow green. I'm not good in color. Then Malkasa by a blue or something by this color, and Raya is designated by a pink. So by this way, you can also create amazing or interesting by plots. Then again, if you want to scale, that means increasing the size of the graph, so you have to use this scale. So just simply you have to use a PCA ellipse equals to true, but here is observation scale is equals to true. You can change into 1 or 3, whatever you want. Then the variable scale also you can add, you can change in this way. Then the labels equals to the row names of the genotype or our data, and again here is group is environment. So type this, then you will get scaled by plots. Yeah. Moreover, if you want to remove the arrows altogether, so you have to type here. All things are similar, but come here the variable axis is equals to false. So all the variable, that means the pH, the GY, the SL will be removed from our biplot. Yes, as you can see here, only the genotype is seen in this graph. Then finally, if you want to create a customized biplot, so you have to use the ggbiplot, then a PCA, then ellipse equals to true, then observation scale is equals to 1, and you can change it to 2 or in 3, and the variable scale, that means planted scale is 1, labels, that means the row names is equals to our data, so that will get our genotypes, and the grouping will be using the environment plus scale color manual. Then name, you can give this name, for example, Raya, Adit, Jimma. They are environment. Actually I referred as environment, but you can change into location or whatever you want. Then the values, that means we have 4 groups, yeah, Jimma, Adit, Malkasa, and Raya. So the first one will be represented by blue, then by red, then by green, then by what? By pink. And also you can give any name that you want here. For example, the title name of your plot. So PCA of Wagjira, so you can change here is Wagjira or any other thing. Then you have to use the temp minimal function in order to get a good background. So by this way you can customize your biplot, and also you have to use legend position either in the top or in the bottom. So type all this and feed to R. So by this way you can get this nice picture. So this is all about the principal component analysis using R software. I hope you get important information and keynotes from my tutorial. And as usual, don't forget to provide your valuable comment, suggestion, feedback, any other things through YouTube comment box or through my email. So thank you for watching and have a nice time.